Hello and welcome to my first ever video of the Infinite Nil channel. There are some old videos of my old software, but I've decided to start recording some tutorials and other things. I have been experimenting with AI assisted development and trying to get into that. And I decided to do a new project completely using just Claude Code and Agentic coding to write a Lisp. I've always been fascinated by Lisp. I basically spent a year with Common Lisp in college and grew to really love it. And I've always kind of wanted to use it. And only now are languages catching up with everything that Lisp provided. Now you're seeing mainstream languages have macros, not nearly as elegant as Lisp macros. But anyway, that's why I'm interested in Lisp. And I spent a lot of my time since 2003 in the Apple community, Apple development community. So I also dabble in Lisp and write mobile apps a lot. And so I wanted to write a Lisp compiler or a Lisp interpreter / compiler that works with Swift. This compiler or interpreter will be very, very heavily inspired by Clojure as far as syntax go, and maybe even functions and whatnot. But eventually the goal is also to be able to either embed a interpreter in your mobile app or Mac app or whatever, or if necessary, you can actually compile it to Swift and just link it into your app. Those are the goals. So I started using Claude Code to start this. I had already done one version of by hand that I had gotten so far with and had paused because I was having second thoughts. But still, that obsession that I have, that need to do this is there. And I also want to learn AI, so I'm going to kill two birds with one stone. So to that end, I did already start, and so I'm going to bring you up to speed with what I have. So here we have Xcode, and this is what I've done so far. I'm calling my language Swish. That therefore the Swish kit, Swish to invoke that it's kind of Swift, but it's Swiftish. It's also Lisp. So that's my name. Anyway, so one of the first things I had Claude do was create a package. And in fact, I'm just opened. This is not an Xcode project. It's just a package. So we have our one of our products is there's the SwishKit library, which you could import into any Swift program. And then we have a command line app called Swish that we use as a REPL for now. Eventually we'll add more arguments and commands to it. For now, it's just a REPL. So it created this for me. And then also eventually I told it that my REPL needed to be able to bring up previous commands and edit the commands on the prompt. And I had kind of done that before with a line noise package, but it didn't satisfy all my needs. And Claude came up with this command line kit, which I wasn't even aware of. And now my REPL fully supports being able to edit your input and bring up previous commands, and it's really nice. So that's something that I may or may not have been able to do with Claude. Certainly not in the length of time that it took, which is like, I don't know, mere minutes. So anyway, let's go over what it has done so far. You can see that it's written a whole bunch of tests. In fact, let's just go run the REPL. So here it is. It's Swish, and you can type help and it'll show you your commands, and you can quit. You can use /n. You see the lambda 1, that's the number of the command. So if I type a number like 13, it just evaluates to itself, and now it's 2. So now I can go back and say 1, and it'll bring it back again. So right now the REPL only supports typing in literals and evaluating. They evaluate to themselves. But we have support for regular numbers. You can put underscores in your numbers. You can enter things in hex or binary. There is error. Oh, that's a bug. Shouldn't have done that. Actually, what happened there is it recognized 0B11 as a number, and then it recognized 222 as another number and returned the 222. Still a bug that it didn't recognize that that was supposed to be one number and not two numbers. So, but if I enter 3A, again, we got the same problem. But if I enter a common, it's going to get me. That's an illegal character because nothing composes that. So anyway, where were we? We've got binary numbers. We've got octal numbers. And you can see that it's converting that to the decimal number of that when it evaluates it. What else do we got? You can enter exponents, including negatives, negative numbers. We've got strings with special characters. We've got multi-line strings. And you can see that the REPL also supports that if you don't finish an expression, it lets you finish it. So we can enter multi-line expressions, and there you get that expression. We've got single character literals like Clojure does. So you just precede that by a slash. And I just implemented lists. So in Lisp, lists are surrounded by parentheses. So I can put a whole bunch of literals in a list, and they don't have to be the same type. Right now, everything evaluates to itself. So you won't be able to do this in a normal Lisp because lists in Lisp get evaluated differently. So that's the REPL right now. So if we go, let's look at the code. I have not written any of this code. I maybe changed some text once, but all of this has been done with Claude. So, and I really haven't had any issues. It's worked really well, and I think the secret to that is how I set things up. So when I first created this project, I added this Claude MD file, and you can see there's a description of the project. Let's turn on word wrap for this. So here's a description of the project. Swish is a Clojure-like Lisp implementation designed to integrate seamlessly with Swift and Apple developer ecosystem. The goal is to bring Clojure's powerful features, persistent data structures, functional programming idioms, homoiconicity, and macros to iOS, macOS, and other Mac platforms. So, and in the code style, I say refer to this other file for Swift and Swift UI guidelines. Other things to be built in later, and then I also tell REPL commands are preceded by the /. And when it did that, I told it remember that in this file. So then if we look at Swift, which is probably the real key to the thing, and I can't take credit for all of this. This actually comes from the Swift agents file that Paul Hudson created. And I'll put the URL in the show notes. But yeah, this has everything you need to write good Swift code. which to target, which version of the language. Use observable when doing Swift dies. Don't use UI kit. All these things that are used that you should do with modern Swift. I added this one to define functions after use and not before, because that's how I like to do things. I also added this section on formatting Swift code because I like my else's like this and my catches not cuddled. And I also like new lines between my case statements. So I added that as well. And sometimes I've found that Claude will forget to do some of these things, and you'll have to tell it, remind it. Here's another one I added. I like to avoid explicit returns if I can. So more stuff from Paul's file, how to do proper Swift UI and Swift data and what your project structure should be like, etc., etc. And here's another key one. I think I added this. Apple, hidden deep inside Xcode, is their own documentation for LLMs to use, and it's located at your Xcode apps. Deep in there, contents, plugins, IDEIntelligenceChat.framework, versions, resources, and then additional documentation. If you go pull that up, you'll see a whole bunch of LLM docs that you can use. So, let's look at this code. And again, Claude wrote this code. Some of these files are too big for my taste, but I'm kind of just trying not to worry about the code and let Claude handle it. Much like how we don't care how compilers generate the code, I think that's going to be the future, where we don't care too much about how AIs generate the code. So here's the main program. You'll see some setup for ASCII sequences for our terminal. The main program, Swish is our interpreter. The printer is how we print results and print a banner. We get the main prompt. We get some input. You'll know that continuation needed is where it handles, whether it needs you to enter more stuff after you've entered one line. And it also here, it's looking for some commands, substituting results if you've asked for them. Here's the main line where it evaluates what you've typed, and it keeps track of the results, and then it prints out the result using the printer to print it, or an error if you had an error. So, and just a REPL is called a read eval print loop, and it just keeps looping until you quit. And there's the continuation need function. So all this code was generated by Claude, and yeah, it works. Let's go to Swish, our library, Swish kit. We'll start with, I don't know so a compiler is typically divided into a bunch of phases. A Lisp interpreter compiler is no different. First, you have the Lexer, which takes a raw input string, and it's going to convert it to a series of tokens. So here you can see tokens. It's going to recognize that there's an integer, float, ratio, string, characters, booleans, nil, some keyword, a symbol, keyword. I didn't show some of these. Let's go back. So a ratio, most languages don't have this. It's a fraction. Lisp will let you represent things very accurately if you want to use ratios. Instead of having 2 divided by 3, it's going to be sort of 2/3 or 3 seconds or whatever. That's a ratio. And if you type it in, or it reduces it, so that reduces an integer. But if I reduce it to here, it's going to reduce to 10/3. Well, that's not a good example. Let's do 5, 10, 4, and I'll reduce it to 5 seconds. So we've got booleans, we've got true and false, we've got the nil keyword, we've got symbols, which we'll later use as identifiers, and they're just like Lisp, but you can put all kinds of characters in here. And of course we've got keywords are just symbols preceded by that, and left and right parameter for Lisp, so that covers that. So we've got our token types, and then each token has the type, the actual text associated with that token, and the line and column where it occurred, and it's used in error reporting. So we've got and then we have a bunch of Lexer errors, and basically the Lexer is mostly this one function called next token that the parser is going to take and to get the token, and there's just a bunch of code here to recognize all the different tokens, and you can see there's quite a bit of code to scan this out. This, in my opinion, this could be split out a little more, maybe into different files. Some of these methods are kind of long. You saw we have methods to scan a string and scan an octal integer and a binary digit, all these things that it's put in that you would do as a human. So it's doing pretty much in line with what I did in the original, except I'm able to take the time and implement parsing hexadecimal numbers and octal numbers and numbers with underscores and all that stuff, all the little details that modern languages have. Unicode characters, we support Unicode characters, so you can type /u and you do like Swift and you put them in curly braces. 28C, this will be the Euro character, and you see there we have the Euro character. So they're scan Unicode characters, determine which characters can start a symbol, scan the symbol, scan keywords. So that's the tokenizer, or the Lexer. That's another name for it. Then there's the parser, and the parser is going to use the Lexer and ask for each token, and it's going to take a bunch of tokens and parse them out and convert that into an AST, an abstract syntax tree, which in our case here is represented by an EXPR, an expression. So right now we just self-evaluate, so everything kind of evaluates to itself or is represented by itself, and this is how we are representing these things in memory. So a list is an array of expressions. And we have our parser errors, and there's the parser, and we initialize it with our Lexer, and there's parse, where it just goes through until it gets the end of file token, and it parses each expression. And so a valid program so far is just a single expression, so, or a bunch of expressions, I should say. So here's our parser. If it gets an integer token, it parses them as different, whether they're octal, binary, whatever. Throws an error if it can't represent it, if it's too large, whatever, and returns our expression, our AST, and then advances to the next token, etc., etc. Again, these are things that if you were writing by hand, you would do the same thing. So here we are parsing lists, we're parsing hex integers, parsing binary integers. Advance just means go give me the next token. That's that. So the next step is the parser returns this array of expressions, our AST. That will get handled. Actually, let me go back a little bit. You saw that the REPL was invoking this, creating this Swish structure. That's our interpreter, and it calls this main function here. So this gives a good overview of what it's doing. creates a Lexer, creates a parser with the Lexer, parses everything, checks for errors, and then it's going to create this the evaluator, and it's going to go through every expression and evaluate it and return the result of the last expression. So now we can look at the evaluator. Evaluator is actually very simple right now because, like I said, everything evaluates to itself. This will change shortly as we build things out. And then find the final result of the REPL that you saw was a printer. And the printer takes one thing you'll know is the evaluator takes in the AST and expression and spits out another AST, actually another expression. And this is how lists work, in that you represent the code by the code itself. Data can be represented by the same code. This gives Lisp its power, makes Lisp very easy to write macros, relatively easy, I should say. So Lisp's AST is Lisp code itself. That's why we just basically, you're going to simplify whatever AST they give in. You're going to evaluate it, and it results in another more simple AST. So now, as I said before, the REPL is going to get that result and it's going to print it out. And we have different ways of printing out different things. So here's a print string. Print string is the main function of the printer. You give it an expression, and based on that expression, it prints it out in different ways. So some helper functions, print characters, print escape strings, etc. And that is it for as far as our reps, what we have so far in the REPL. And you'll see here, then we have a bunch of tests, lots of tests. I think there's about 300 tests now, where the Claude created these tests that every time I ask it for do something, it will write new tests for the new functionality, and it'll make sure all the tests pass. And one thing I've heard is you have to be careful that it doesn't just modify the tests to make things pass, but so far it hasn't done that. So lots of tests for scanning and whatnot for the Lexer. I think the Lexer has the most amount of tests. And then we have the parser tests, where again we test how it parses certain things. Bunch of stuff there, and then we'll have evaluator tests. Again, things are just going to evaluate to themselves, so it's relatively straightforward. And then finally, I think we have some printer tests, where we make sure things print out as we expect them. And for some reason it broke out special tests for working with ratios. I think that's because it created its own ratio structure to represent our ratios. And then we have tests to test the whole interpreter flow. And there we go. So that's it for this episode. I just wanted to give you an introduction to the project and what we've done, what I've done. Going forward, we are going to continue vibe coding this. It's not really vibe coding because I'm doing one step at a time, making sure it does it right, making sure it tests, all that stuff. And so our next step, we've got lists, we just did lists, and now I'm going to add support for the def key in Clojure. And it's a way that you can define variables or declare variables. And I'll go more into that in the next episode. So stay tuned for that. I hope you enjoyed this. Talk to you later.